This is 416.15. And these are Chapter 11 notes, having sort of blasted through notions of diatomicism and Avogadro and Gay-Lussac. We'll leave that where it is. Here's the question I have for you. If I have some, oops, I'm drawing that upside down, some gas, let's say I've got it encapsulated in a nice balloon. I have some amount of, pick your gas, CO2, N2, whatever. I've just got a sample of gas. And we've been working with problems concerning pressure, volume, and temperature relationships in gases and how they behave. And you know that if you change the volume, the pressure changes, and the temperature changes, and if you change the temperature, the other two change. And if you hold one constant and change one, the third one changes. Great. So let's say that we have this sample of gas, and we hold the pressure constant, we hold the temperature constant, but somehow the volume increases. How's this possible? And this is one of the questions on your what do you know. We should actually go back and revisit that, shouldn't we? Let's go visit that, shall we? So as a few of you said it, if the pressure and temperature are held constant, but the volume changed, then there must be a different amount of the gas in there. There's a factor we haven't been talking about. If everything else is held constant, but the volume still changes, the thing that must have changed that we didn't talk about yet is the number of moles. Number of moles of the gas. So in the last chapter we were really talking mostly about the physical behavior of gases. Now we're going to start to talk about the molecular nature of gases. So we're actually going to talk about how gas molecules behave, and we're going to blend what we know about the physical behavior of gases with stoichiometry. So this is a factor we haven't considered before. In the last chapter we always assumed that it was a stable amount of the gas. It was the same number of molecules of a gas. And now we're going to start to change that. So this is Avogadro. And what Avogadro says, he had a lot of things to say actually, is that gas volume is directly proportional to the amount of gas. So if the number of moles of the gas goes up, the volume of the gas goes up. If the number of moles of the gas is reduced, the volume of the gas is reduced. It's pretty easy and it's pretty basic to understand. Now, there's another neat thing. So the mole is really kind of an interesting unit. Conceptually we have this number of things that we call a mole. And it happens to be a number of things that add up to the molar mass of. So it's almost magic to me that we can take this atomic mass, and if we have this many things of it, we have that mass in grams. It seems weird and mystical and too good to be true. Well, it gets weirder. So if we have 1 mole of oxygen, 1 mole of O2, at STP, it will have a volume of 22.4 liters. Oh. Okay, so what? Who cares? Well, turns out if we have 1 mole of CO2 at STP, guess what its volume is? 22.4 liters. Wait a minute. O2 and CO2 have different masses, they have different rates of diffusion, they have different all kinds of things. They're not the same gas. You can't fool me, Moser. That's true, I can't. 1 mole of, let's pick a really nasty gas, radon, and really heavy. Like way down there, the noble gases, big, heavy molecules. Okay, well, 1 mole of radon gas at STP has a volume 22.4 liters. Does this seem wrong to anybody? But it's not. It's true. So this is what we call standard molar gas volume. It's a molar volume of gas. Any gas at STP has a volume of 22.4 liters. Okay, so it seems weird, it seems like it's wrong, but the reason it's possible, remember, in a gas, those molecules are spread out very distantly from one another. They are spread pretty far apart, and so it's the amount of space they take up, their density has less to do with their mass or their speed than it does the pressure and temperature they're under. So pressure and temperature really controls volume. And so 1 mole of any gas you can name at STP is going to take 22.4 liters of space. Now the cool part is that means we can use it as a conversion factor. So we can do things like this. So we'll start off with the simplest ones, like number 1 on the bottom of 336. So we'll do that. At STP, what's the volume of 7.08 moles of nitrogen gas? Because we see the words at STP, we can do this. 7.08 moles of N2. 1 mole of N2 has a volume of 22.4 liters. Now, what I typically do for myself, because I will screw these up if I don't, is I will write here at STP, somewhere near where I'm starting that factor label, because if it's not at STP, this relationship doesn't hold true, and you can't use that conversion. So I tend to jot that down someplace for myself, because we will run into ones where you can't do that. Whoa, not logarithm. Okay, what do you get for a volume? Okay, so we get a raw answer of 158.592 liters. We have 3 sig figs. This will be 159 liters of N2. Okay. That's pretty easy. That's really easy. So let's do one that's slightly more interesting. Okay, here we go. So this is number 3 at the top of 337. So at STP, a sample of neon gas occupies 550 cubic centimeters. How many moles of neon gas does this represent? So it's straightforward, except that we have to do a conversion to start off with. So we're given a volume in cubic centimeters, and we have to translate that into liters if we're going to make sense of this. So 1 cubic centimeter is equal to 1 milliliter, and 10 to the third milliliters equal 1 liter. So that'll get us to liters, and we can just keep rolling from there, because what we want to know is how many moles this is. Well, we know that and this is at STP, so I'm going to jot my little at STP here. 22.4 liters is 1 mole. So now we can go from there to get a raw answer. So we have a raw answer here in moles. We actually have 3 sig figs. That given in the book was 550 with a decimal after it. So what would that answer be with 3 sig figs? This is one of the ones everybody hates. That's 1 sig fig. 0.0, that's 2 sig figs. That's 3 sig figs. Leading zeros are not significant, remember? Leading zeros are not significant. So that's 3 sig figs. So 0.0246 moles. You could always express it in scientific notation if you wanted. So, okay. Not bad. Let's do one more, and then I'll turn you loose to practice on the rest of these. These are easy enough. We may just do a FIP tomorrow, and those of you who aren't here can take it on return. So, okay, let's do the practice number 1 at the bottom of 337. So, what is the mass of 1.33 times 10 to the 4th milliliters of oxygen gas at STP? Well, we have our given 1.33 times 10 to the 4th milliliters, whoops, of O2, and we want to get to mass. So, we're going to use that molar conversion factor. And again, we need to be in liters. So 10 to the 3rd milliliters is 1 liter. And then we can go from liters, because we're at STP, 22.4 liters is equal to 1 mole. And we can get the mass of a mole of oxygen gas. What's the mass of 1 mole of oxygen gas? It's O2, be careful. 32. 32.00 grams. Okay, so we've got our setup, and now we can go get our numbers. 19 grams, really weird and really even. Very weird and very even. Now, we have 3 sig figs. How do you make that 3 sig figs? Huh? Yeah, 19.0 grams gives us our sig fig. Okay, I would recommend doing the other practice problems. There's 1 more in the first chunk, and there are 2 more in the second chunk. And I'll put some homework problems up for people to practice on also. That's it. FIP tomorrow.